So for the next problem, I want to show you a more complicated ternary phase diagram. So this is SiO2, MgO, and Al2O3. And this is a fairly common phase diagram for people working in the field of ceramics. Some of this is a little bit more complicated than what we worked on last week, so I'm not going to read a cooling curve from this, but I'm going to set it up so that you know the next step in calculating a cooling curve. I've got one of these that doesn't have marks on it. So if I were to give you this problem, this phase diagram, and instead gave you some composition, well, you want to know, as you cool down, what phase forms first. So you want to identify the liquidous surface you're cutting through. And that's relatively easy because this phase diagram comes, it comes marked. It also has the isotherms. The question though is, where does it wind up? Right? Because remember, we talked in class on Wednesday, and we said that as you cool, you start out and you know the phase field, or the compositional triangle where you sit, but you don't necessarily know, but if you know the compositional triangle where you start out, then you know that the eutectic point that you stop, that is going to be determined by the three phases on the corners of that compositional triangle. So what I want to show you here is how to identify compositional triangles. So let's start with relatively simple points. I'm going to draw this in. I'm going to draw the points here in binary. So we have all of these labels. I want to point out also here that cristobalite and tritomite, those are both the same composition. So in this phase diagram, this region is all the same, even though there's a little indicator there. Otherwise, it's just a polymorph that is not important. So here we've got periclase, foresterite. I cannot pronounce these for anything. This foresterite and spinel, and we have the compositions of those listed. But look, we've got a triple point where those three form, and that tells you that those are going to form a compositional triangle. So we can draw a line between spinel and foresterite. And you know what? I might change colors here. I thought I was going to draw it in black, but that's going to confuse the diagram some. So let's draw our compositional triangles in red. Okay, so spinel, foresterite, and periclase going to be connected like this. And then we also have these edges as part of our compositional triangle. That. That's one compositional triangle. And these are our Alcomate lines, because the Alcomate line are lines that are drawn between two phases that necessarily have a two liquidous lines that are shared and are common. So if you look here, let me zoom in. Oops, zoom in you actually see that they draw an arrow here going to the, an arrow here going down, an arrow here going down. So that means that if you start out in this compositional range, say right here, and it comes down and it goes to that three-phase region, well, then it's going to go down. Because remember, where the alkemade crosses this liquidus boundary, that is a maximum. So it's going to come down, and we will have a final composition at that eutectic. If, on the other hand, you start out, I'm going to zoom out a little bit here, in this region, say just slightly to the right, well then you'll go to that boundary and then go downhill until you reach that triangle. And that triangle, connects spinel, forsterite, and corderite. And corderite is right there. So we can draw this compositional triangle. So this is another compositional triangle. And I'm gonna color these so you can see that anyone in this starting in this compositional triangle will necessarily end at that point. Anyone starting in this compositional triangle with spinel, corderite, and forsterite, they're going to come down. They will stop at that point. So something to note here is that that point is outside of the original compositional triangle. So this is going to behave a little bit like a when you think of the paratectics, right? So we're going to talk about this later in the week. Sorry, so we got two compositional triangles. Other compositional triangles that we can identify. Well, here's a point that has spinel, corundum, and molite. So here's spinel, corundum, and molite. Let's draw a compositional triangle here. Okay, so this compositional triangle, which I'll draw in lavender. Anytime you start here and you cool down, it's going to ultimately stop here. So that's quite a ways away. But that's the triple point of the eutectic that we're going to form. Let's look at, what else do we got? Well, that little triangle, you can see right there, that is Zephyrine, I guess. So somewhere we have Zephyrine, molite, and spinel. So let's see. Here's Zephyrine, here's spinel, and here's molite. So that means that this compositional triangle here is going to wind up solidifying here. So that's kind of interesting. That means that if you were to, say, start with a composition here, just on the right-hand side, you start out with corundum and liquid, and cool, and eventually come to here. Or I guess you'd cool and come to that edge and stop at that triple point. If instead you were just across that border, then you cool, still form corundum and liquid, here form corundum and molite, come to that point, and then keep going until you get to that eutectic, and that's the point that you would solidify. Okay, let's identify some more of these. That point is sapphirine, molite, and corderite. So let's see, corderite is there, molite is here, sapphirine is here, so that means this. Compositional triangle. And I'm going to make that orange. So that compositional triangle has eutectic, molite, sapphirine, corderite. Right there. And then the other final little point, let me zoom in. Final point, which is right there, that is corderite, spinel, and sapphirine. So we have spinel, corderite, and sapphirine, and I'll put that in, just pick purple. So if you start in this compositional triangle, then as you cool, you would eventually stop at that point. Yeah, zoom out. Oops. So here's our spinel, sapphirine, corderite, and we come to that point. Okay, so we've pretty much filled this all in. We still have a few that we haven't addressed. So let's go back and do those. We've got that one covered. Here's one which is statite, forsterite, and corderite. So we've got corderite, forsterite, and statite. Okay. So, light green. This compositional triangle is going to have its eutectic right there. And now we've got enstatite, tritomite, and corderite. So tritomite, corderite, and statite. There, and there. So using gold. Anything that forms with this compositional range, it's going to cool down and it's going to make it to here. So that's a well-behaved eutectic, similar to what we just looked at here, right? Great. And the last region that we haven't yet identified is cristobalite, corderite, and molite, which I'm going to do this in is maroon. And somewhere we have a triple point. Here's tridymite, corderite, mullite. There. So now we filled in the diagram, so we know that for any composition that we start out with, we know where it's going to wind up. And we also know that if I wanted to, I could give you a problem identifying compositions in this. So for example, I can pick something that starts out in this region of the diagram, and you could easily talk about the solidification. So for example, let's say I gave you a composition that started out right here. Well, if you had a composition that started out right there, how would you talk about the solidification? Well, you talk about the solidification by first saying, okay, cools down, where do we draw our tie lines? Well, we have corderite plus liquid, so that's corderite. So our tie line would be drawn between the composition and the solid forms. And let's say we have a tie line that does that. And we say, okay, what's the fraction of solid? Well, the fraction of solid, which is the corderite, we measure, and we measure that. It's going to be like 5 millimeter divided by, what is that? About 20 millimeter. Right, so that tells us that's around, 25%. Solid, which means the fraction of liquid is 0.75. We say, what's the composition of the liquid? Well, we can read the composition of the liquid. It's at that point, right? Is this the point on our where the tie line touches the liquidous surface as given by the isotherms? And what you could do is you could use the compositions here. Oh, sorry. You can use the compositions on the corners, and you could actually do this, like that. To determine the composition of the liquid. Another thing you could do is, if you knew the chemical formula of enstatite, corderite, and tridymite, you could just work purely in that phase, compositional phase region, right? And what we could do is we could draw lines. I'm going to pick a new diagram here. Statite, corderite, and we can work purely in this compositional. We can work purely in this compositional triangle. So I've said I was here. So this is 1365 degrees C. And what we could do is we could draw parallel lines. That. So now we know that we are, let's see, fraction SiO, so composition of liquid. We know that we are measuring here to here. That gives us around 67 and that point, the intersection point. So that's around 11 SiO2, and then drawing a parallel line here. Yeah, I used to be an engineer, huh? My parallel lines could use some help. So that's about 550. This distance is around 11. In statite. And then this distance that's 50 divided by this distance is, see, it's around 30 of corduroy. CORDIERITE. So if you knew the chemical compositions of a statite and corduroy, you could use this compositional diagram to determine the composition of the liquid. Now, kind of continuing the discussion of this diagram, we had our tie line, which I'm going to put back here in green. We had our tie line. And it keeps going. And let's see, I picked, this was my original, that was my original composition when it was of the entire system at high temperature, cooled down. And then as we solidify, we know then that just prior to forming the eutectic, we would have liquid that's determined by, well, it'll be right here, and the phase fraction would be determined by drawing the tie line pivoting around our original composition. So this tie line touches the liquidus here, and it touches the phase boundary here. So by measuring this distance, that's going to be, what did I say, it was going to be 67. And then this distance here is around 5. So that is, this is a solid. So just prior to solidifying the eutectic, we have or 5 divided by 65 SiO2, and then that gives us 62 divided by 67 of corduroy. That forms. That's the of the solid, and the solid itself at this point, fraction of solid is, what is that? That's around That's around 20, and that's maybe 11 over 20. So fraction of liquid is 9 over 20. So just prior to forming the eutectic, at the eutectic point, we have 9/20 fraction liquid. We have 11/20 fraction solid. That 11/20 fraction solid is made up of 5/67 SiO2 and 62/67 cordierite. So this is an example of reading from a slightly more complex ternary eutectic. So if you're given a ternary eutectic, the first thing to do is to know the compositional range you're looking at, and within that range, identify the compositional triangle that you're sitting at and the eutectic path or the cooling path that you're going to be following.